Hi everyone, and welcome back to another AP Calculus video. In this video we're going to talk about integrals as net area and relate them to velocity, acceleration, and displacement. And so at this point we should be fairly familiar with the relationship between velocity and acceleration and velocity and displacement. So if we consider this curve created by this velocity equation, this would be our v of t. And so the derivative of v of t would be found by, sketching all these little tangents. They'd be the instantaneous rates of change all along our curve. And we should also be familiar from previous units with the idea that if I find v prime, that's the rate of change of a velocity. We call that a of t, the acceleration. And then we should also be familiar with the idea that the area under the curve represents displacement. And the displacement, sometimes we refer to that as s of t, or my position curve. So when we find the area underneath, that's a process that we've learned called integration. And so if we integrate our velocity, that's called our displacement. So we have this relationship with velocity, and if we're given a curve, the first thing you always want to do is you want to ask yourself, what kind of a curve is this? Is this a function? Is it a rate of change? Is it an acceleration? Is it velocity? Always wrap your brain around that. And what I do is anytime I'm given a velocity curve, if this is velocity, then I write down a couple of relationships. I'm going to record that if this is velocity, then the derivative v prime would be my acceleration. So I write down and I try to relate any and all other equations that could come up in a problem to my curve, to the thing I have. And I'll also write down that, when I integrate it, it's going to be my displacement. So when we encounter these graphs on an AP exam, being able to relate them back and forth with the derivative as well as the antiderivative or the integral, depending on the situation. And let's go ahead and make sure we understand that's an integral from a to b. It's a definite integral. Anytime we're given a curve on an AP exam, we always want to write down as many relationships as we can. And it's not always going to be velocity, acceleration, and displacement. Sometimes you're given functions in other formats. So being able to relate them backwards and forwards, in a sense, to the derivative and to the integral, and recording those relationships could earn you points on an AP exam. So now that we've kind of established some of these relationships, let's go ahead and record them. What would we get if we found v prime? Well, if v is measured, and let's go ahead and assign it some units. The velocity, we'll say it's meters per second, because it doesn't specify. So if we are in meters per second, if we found v prime, that would be my acceleration. And the units would be meters per second or meters per second squared. So as the acceleration, you can write it as meters per second squared. Not every situation where you're finding an acceleration or a rate of change can be written this way. So writing it, this way is always good. But when it's specifically strictly acceleration, you can write it as meters per second squared. It's not always going to be that easy, though, if it's not velocity. And the next question says, what does the integral give us? This gives us displacement. And the displacement would be measured in meters. Okay. And then if I were to integrate specifically from 0 to 5, this would be the displacement in meters for the first 5 seconds. So understanding and being able to interpret what the integral means is a key concept that could come up on an AP exam. So understanding the relationship is critical to being able to solve these problems. So let's take a look at some definitions. We've talked about this word displacement, and a displacement is a change in position from start to end. It can be positive if the final position is forward or to the right of the beginning. It can be a negative displacement. Basically, it's how much did you move over this course, over the period of time. It can be 0, and just because your displacement is 0 doesn't mean your object stayed put the entire time. Displacement is something that I like to talk about in terms of how you start your day. Generally speaking, we start our day getting out of bed. And generally speaking, we start our day getting back into bed where we started from. And so your displacement throughout the course of a day is more than likely 0. The total distance you travel, though, doesn't take into account the direction that you traveled. You see, displacement considers any motion to the right or forward as being positive motion, and any motion to the left or backwards as being negative. So through the course of the day, as you leave your house, that could be positive velocity or movement in the positive direction, and then as you return, you're basically canceling out all of that movement with negative direction. And so displacement considers the directional nature of velocity. Total distance says, I don't care which way you went, I'm just going to measure your steps. So a great analogy for this would be the step counter on your watch. Your step counter counts the total distance or the total number of steps you take throughout the course of a day. It doesn't take into account positive or negative direction, and it just says, hey, you traveled this much. So total distance is everything's positive. And oftentimes, we talk about total distance, we say TD for, a fun little trick to remember. Total distance, TD is like touchdown in football. And what do you do when you get a touchdown in football? You put your hands up, right? If you're the ref, you're like, touchdown! Well, we think of these hands as being our absolute value bars. So really, the total distance is the absolute value of that velocity equation integrated from point A to point B. And even though I have indefinite integrals listed here, really, truly, they would be definite integrals. And so we should have an A and a B kind of floating in there. So from time A to time B, that's my displacement or my total distance. So if we reconsider this graph, we want to describe our motion of our particle given here. So remember, this is a velocity curve. So this is v of t. And so as I travel my velocity curve, I'm going to remember that I have negative velocity down here. So anytime I have negative velocity, it means I'm moving left. So we'll use left and right. You could also use forward or backward. We'll just say left and right. So we're going to say that this particle moves left from t equals 0 to t equals 1.255 as shown on the graph. The particle moves left. Then stops and changes direction and moves to the right. So here we're moving, here we have positive velocity, so we're moving right. Here we have negative velocity, we're moving left. The other thing that we can take a look at is, as we examine what's happening with the velocity, as it, increases or decreases, we could talk about slowing down or speeding up. And one of the things that we look at when we look at a graph is this concept of if my velocity, if I have positive velocity and positive acceleration, so that's v prime. So over here, I have positive acceleration the entire time. So my acceleration is constantly, the slopes will be sloping upward, a positive slope. So throughout the entire graph, my acceleration is going to be positive. So v prime, the derivative, is positive because my graph is increasing. When you have a function that's increasing, its derivative is positive. So we have positive acceleration the entire time. Anytime you have positive velocity and positive acceleration, if the signs are the same, then my object is speeding up. The same can be said if you have negative velocity and negative acceleration. So these are the time when my particle is increasing in speed, it's speeding up. If you have opposite signs, so positive velocity, negative acceleration, or negative velocity and positive acceleration, now we're slowing down. And the reason is that acceleration is also a directional movement. It's a directional thing. So when it's positive or negative, that acceleration, that force of acceleration is working in a certain direction. And if your velocity is working in one direction and your acceleration is working in the other, then they're fighting each other and you would be having an object that's slowing down. So the other way that we can describe this graph is anywhere we have positive acceleration. So here we have positive acceleration, positive velocity, we're speeding up. Here we have negative velocity, but our acceleration is still positive, we're slowing down. Okay, so one thing we can add here to our description is that on the same interval that we're moving left and slows down, then changes direction, moves right, and speeds up. So understanding that convention of same sign, speed up, opposite signs, they're working against each other, your particle is going to slow down. So now we want to know, what is the displacement from 0 to 5? Well, this is when we're going to set up that integral. So as we set up our integral, we're going to integrate 0 to 5 v of t dt. Now here's the cool part about these types of problems. My velocity has been defined as v of t, so I don't need to write that equation in when I set up my integral. And anytime I'm doing a problem with my calculator, I want to make sure that I record the integral that goes into my calculator. It's really critical that we record the integral that we're using. You don't have to write the equation out. If it's been defined as v of t, you can just use v of t, so you don't have to write the entire equation. But now what we're going to do is put it into our calculator. So to type this into my calculator, I'm going to use my math9 function. So math9, and this allows me to enter information into an integral. Now if you have the older calculator that says FNINT, then the convention you're going to use is you're going to type in the equation first. So I'm going to go ahead and type this equation in. I'm going to use the x variable instead of t, because that's what my calculator, that's the language my calculator likes to speak. And then notice I like to be very liberal with my parentheses, especially if you're unsure if you need them or not. Generally, you need them. It never hurts to put those parentheses into the problem. So if you have the older one, it goes FNINT, then you're going to enter the equation and with a comma, and then you're going to enter an x, and then a comma, and then 0, 5. So it's function, variable, a, b. In this format, the newer one, it's nice and easy. You just make it look like what's on your screen. And here's my displacement, 35. So I have gone 35, and assuming that this is meters, I've gone 35 meters during this time period. Now it's important to understand that the 35 meters is my displacement. I probably traveled more than that, but what this 35 meters tells me is that moving left and moving right, when you combine all of the distance, now clearly I went more distance during the positive phase, but from 0 to 5, I have more displacement in the positive direction than I do in the negative. So what that integral did was it said, hey, this negative area underneath is going to cancel out whatever negative area up here, and so this amount that's left is my 35 that I just got. So it's important to understand how these integrals work. Now the last question here says, what is the total distance covered during the first 5 seconds? And this is kind of tricky. I'm going to show you 2 ways to work this out. The first way that we can do this is we can split the integral. And what we can do is we can find from 0 to wherever it hits that x-axis. So 1.255. This is a value you could solve for on your calculator. You could find this area. And knowing that it's going to be negative, take the opposite of it, and then add to it the positive area. The other way that you could do this is you could enter it as an absolute value. So I will show you both on the calculator, and we'll see that they both produce the same result. So taking a look at the results when we put the integral in, you'll notice that my limits of integration go out to quite a few more decimal places than what the Desmos graph that I snipped into my notes allows. And one of the things that I did was I actually went and I put the equation into y1. So here's a little trick and a tip that I can give you so that you don't have to continue to type a complicated function into your calculation screen. If we put it into y1 and graph it and then use our calculator to calculate a 0, it'll actually spit out our 0, and you can see that I went through it and I have a screenshot here. Here's the actual 0, and that's the value we actually want to use. We never want to round our limits of integration to 3 places. We always, always, always want to make sure that we're using as many decimal places of accuracy as possible. So 2545447, I'm going to use all of these decimals, 2545447. And if you're going to find that you're writing these down a lot, sometimes it's nice to just say, hey, I'm going to define this as C, 1.2545447. That's a nice little tip that you can do. And then instead of writing these in, you know, it's perfectly acceptable then, provided that you define it within your workspace. You know, and if you go on and if you use it in part A on a free response, make sure that you carry that down and redefine it for part B or part C or wherever, so that the AP grader can see that. But basically, you're going to integrate, and if we take a look at our calculator and what our screen shows, you'll see, here's our screen, you'll see that we're slightly off, and that's because, again, this is rounded, so it's not exactly precise. But you'll see then the nice part about putting it into Y1 is that you can always recall a value by hitting alpha trace. And there's your variables, and if you know it's in Y1, then you can just recall it very quickly. Now, just a side note to get to the absolute value function, if you're unfamiliar with that, it's in the math option, and if you go over 1, there it is, absolute value. So math over 1 to numerical, and that'll give you quite a few options. It's always kind of fun to explore those menus. But these are the two values, so about 42.587 is what I'm going to write down, 42.587. And that's why we never round to 3 places within our calculation, because check it out. The difference is so minute, and it's several places in. So as long as we're going out to at least 6 places in our calculation, I went to 7. 6 or more is great. The more the better, and the more precision you can get, the more likely it is that when you go to round to your 3 places, you're going to have that accuracy. Because look, right after 4 places, that's where they started to break apart. So as many degrees of accuracy as you can within your calculations, so that when you do your rounding at the end, you have some precision. So now let's talk about the difference between our displacement, or our total distance traveled, those values that we're getting from our integrals, and the question of where does the particle end. So in our previous example, we found that our displacement over the first 5 seconds, so from 0 to 5, v of t dt, was 35. And this was my displacement. In order to figure out where my particle lands, I need to know where it started. Because I have a positive displacement, I know I moved 35 meters to the right. But where did I start from? So the displacement tells us how far the particle shifted, left or right, up or down. If we want to know its position, we need to know where it started. This is called my initial position. And the final position, where I end, is the initial position plus that displacement. So if the particle in our example started at 9, show the integral that represents the final position, and then give its final position. Well, it's going to be 9 plus the displacement. And when we evaluate the integral, we get 9 plus 35, giving us a final position of 42 meters from the origin. So at spot 42. So suppose that this was, you know, some sort of football field or something like that. You started at, 9 meters, and it would be a European football field, right? Because we're metric. So you'd start at 9 meters and you moved the ball in the positive direction 35 feet or 35 meters. And so now you have reached a distance of 42 meters from the end. So this would be kind of how this would play out. So always need to know that, that beginning spot. So what I want to do right now is walk through a free response question that uses a lot of these skills. So this came from the 2016 AB exam. It is free response question 2, so you can look it up and follow along. But you're given a particle for t greater than 0. A particle moves along the x-axis. The velocity of the particle is given by this equation. The particle is at position x equals 2 at time t equals 4. At time t equals 4, is the particle speeding up or slowing down? So this is one of those things where you would have to remember that when you have positive velocity and positive acceleration, or negative velocity and negative acceleration, we're speeding up. And then if they're opposite, you're slowing down. So that's going to be our approach here, since we have an equation. So I'm going to find v of 4, and I'm going to plug that in. 1 plus 2 sine 4 squared over 2, and I'm going to punch that into my calculator. Now, because I can see where this is going, and I'm going to have to use this equation more and more, I'm going to go ahead and just store it in y1. And then if I graph it, I can just find the value by doing second trace and solving for the value there. I can just type in when x is 4, what is the value? We get 2.9787. So I'm going to record that 2.979 and commit that in. So v of 4 equals 2.979. That's v is greater than 0, greater than or equal to 0. And then I need to find a of 4. Well, a of 4 is v prime of 4. So understanding that relationship is going to help me. And by having it already in my calculator, I can go ahead and quit out of this, and I can just do math 8 to evaluate a derivative, d dx. And because it's already in y1, I'm just going to go alpha trace and recall my y1 and put that in there so I don't have to continue typing the values in. So the derivative at x equals 4 is negative 1.614. So I'm going to write that down, negative 1.614. And now here's the explanation I want to give. Since v of 4 is greater than 0 and v prime of 4 equals a of 4, I'm going to make sure that I state that because they may want that, is less than 0, the particle is slowing down. So then if I look at my scoring guidelines over here, it very clearly gives my velocity, my v prime. The particle is slowing down since the velocity and acceleration have different signs. So these were worth 2 points. So now let's take a look at question B. Find all the times t in the interval when the particle changes direction. So what we want to do here is we want to understand when the particle is changing direction, we want to show that the velocity is 0 with a sign change. So I'm going to go back to my calculator, and I need to demonstrate that there's a sign change. And since this is a calculator active one, that's going to be our best way to go. So I'm going to go to my graph, and I need to adjust my window, right? So between 0 and 3. So I'm going to make sure that my x minimum, I'm going to go to -1, and my x max, I'm going to go out to 4. And then my y, I don't really need that to be big, so I'm going to go from like -2 to +2, because remember, I'm looking for zeros with sign changes. So I'm going to tighten my window as much as I can. And so here I am from 0 to 3, taking a look. Oh, and it looks like I've got 1, 2, but that second one is outside of my window. So really, I just have one place where it changes direction. I see a sign change on my velocity curve. It changes direction between 0 and 3. So we're going to find that spot. So I'm going to go second calc, and it's a 0. So I'm going to go down to 0. Left bound says make sure you put your cursor on the left side. So it looks like it's just beyond 2.5, so I'm going to put a cursor there. And then it says right bound, so I'm going to go to the other side, and then I'm going to back it up and give it a guess. I'm going to get between the two spots that I just identified. And there it is, 2.707468. So t equals 2.707468. Now, that's the spot where I found that we're changing direction. So the particle changes direction at t equals 2.707 because v of 2.707 equals 0 and v of t changes direction there. Or changes sign is what I need to say. Changes sign. So let's see what our scoring guidelines have to say about it. So if I go up here to part B, oh look, there it is. V of t changes sign. It says from positive to negative. You don't need to justify that because it's not asking any sort of direction. So as long as you said it changes sign and is 0 at that spot, you get your justification. And as long as you found the right spot, you get your answer. So that was your 2 points for that one. So let's keep going. Let's look at what part C says. Part C says, find the position of the particle at time t equals 0. Now this one is tricky because there's a couple ways you could go about this. But what we need to do is go back and realize that the information we're given, the initial spot is that we're at x equals 2 at t equals 4. So we're actually going backwards, right? So at x equals 2, so at t equals 4, x equals 2. So what we need to do is we need to find the displacement from 0 to 4 and figure out what that is. So let's go ahead and work through that. So the displacement from 0 to 4, I'm going to do that in my graphing calculator. So I'm going to do math 8. And now hopefully you're seeing the value of putting into y1, sorry, not math 8, math 9. It's an integral. So from 0 to 4, what was our displacement? Alpha trace pulls up my y1s, and then dx. So what is my displacement from 0 to 4? It's this number, 5.8150268. 5.8150268. So basically, you were here at t equals 0. At t equals 4, you're at x equals 2. So wherever you jumped from 0 to 4, you took your position and you added this 5.815026. So basically, you need to take your position of 2 and subtract where you came from. So you're moving backwards. So this is the way that I like to think about it. 5.815026. And you end up getting your initial position. So our initial position was negative 3.815. Now, in the scoring guidelines, the setup that they show is slightly different, but essentially it's the same thing. Because they think of this integral, instead of doing from 0 to 4, they integrate from 4 to 0, which if we reverse the limits of integration, it gives us the opposite answer, it gives us a negative value. So in a sense, it allows us to move backwards and provides that negative result. So essentially, they set it up using that formulaic initial position plus displacement, considering that the displacement here is negative. Regardless of how you set it up, as long as you came to the same answer and you set it up and you used either thought process, you should be able to get all the credit. You get 1 point for just setting up the integral. You get 1 point for using that initial condition, and then provided that you use them together, that's where you get the third point of negative 3.815. So now, let's take a look. We can see the answer for D is going to involve some absolute value. Find the total distance the particle travels from t equals 0 to t equals 3. Well, that's going to be the absolute value. Total distance is touchdown, right? So from 0 to 3. So this should be a nice, easy point to grab for this problem, as long as you remember total distance, touchdown. Right? So we're going to go back to our calculator, and we're going to use our calculator to help us with this one. So using our calculator, we type it in, we use the absolute value bars, and we get 5.301 is my total distance traveled from 0 to 3. And this just showing the integral and getting the answer, because it is a calculator question that all you have to do is type in and remember to use the absolute value. It is only worth a point, but again, remembering that it's absolute value and how to get that question. Oh, and actually it was worth more than 1 point. And notice the second point came from the integral. So always, 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 always show the integral and show what you're doing. Anytime you enter anything into a calculator, whether you're using math 8 or math 9, evaluating an integral or a derivative, always show that that's what you're typing in so that the grader can see your work and follow your thought process. No matter where you are in your learning, if this was an easy thing to follow for you, that's wonderful. If it wasn't as easy, that's okay. You just have a little bit more work to do to get where you need to be. And the more you practice and the more exposure you get to these tougher questions, the better you're going to become at being able to solve them and know what they're asking you to do. Through these videos and through my lessons, you'll be exposed to every skill you need to be successful on the AP exam. But it's up to you to take the time to learn how to apply those skills through these tougher problems. So stick with it, keep at it. You can do this. You've got this.